Good morning, everyone. The title of my presentation today is Sprinkler Protection for Non-Storage Occupancies with High Ceiling Clearance. And why am I talking about this, or why was I asked to talk about this? Well, as I travel around the world, it's actually one of the most frequently asked questions I get is how, or even if, you provide sprinkler protection in an occupancy such as a railway station, there we go, rail stations, auditoriums, let's say convention centers, where you have the exhibit halls, sports arenas, where you have very high floor-to-ceiling clearance. For example, in this room, we're at what, about 7 to 8 meters? So no one questions whether you'd use a sprinkler in this application. But what if the ceiling was 2 times this height, or even 3 times? Now people will start to question, do sprinklers, will the heat release from the fire even operate a sprinkler? And so we're going to show some tests that we did in conjunction with the Chinese government, and also Factory Mutual has done 2 test series that address this particular problem. Okay, so let's take an example. Let's say I've got a convention center, and from floor to ceiling, it's 18 meters. What's sprinkler protection based on the current installation standards? And again, as I said, in some countries, they wouldn't even provide sprinkler protection. They'd either do it with building construction materials, smoke removal, or I know in Japan, they'll use a deluge gun and then some sort of detection system that will aim and shoot the water cannon. So, depending on how you would protect this will greatly depend on where you're located in the world. And if we look at some of the current standards, we have EN 12845, which is the European installation standard. We'll protect that with a 5 millimeters per minute density at over an average area of 360 square meters. That's on the low end. Now on the high end is FM. Using its FM global data sheet 3-26, would utilize 20 millimeter per minute over 280 square meters. And you can see whether China, Australia has different criteria. And then I threw in Singapore. Singapore is an example of a country where that's not allowed. Within their standard, they say if you have a floor to ceiling clearance of 13 meters or greater, we can't tell you what to do, okay? So again, how you protect this will depend on the design and installation standard that you choose. In China, they're building a number of these types of facilities, be it airport terminals, convention centers, etc., upgrading infrastructure in many different cities. They were uncomfortable with their protection criteria and really wanted to know what to do. So we ran a series of 5 fire tests at the test laboratory in Tianjin, China. It is, to put it in scale, the facility is about 40 meters wide, about 120 meters long, and it has 2 ceiling heights. One is 25 meters and the other one is 27 meters. So you can see it's quite a large facility and ideal for conducting tests to evaluate these scenarios. In our test plan, we varied the ceiling heights, either 12, 16, or 18 meters. We varied the orifice sizes. We utilized in the first test a K8. That's a current unit. Actually, in the first 2 tests, we used K8. Test number 3, a K11, and in tests 4 and 5, we used a K25 sprinkler. and we vary the discharge pressure out of these sprinklers. The test fuel and fuel array arrangement is very similar to, well, in fact, it is the same as to what Factory Mutual had done in their test series of evaluating the high clearance. And if you're here Tuesday for the storage presentation, I'm sure James Golenville talked about this fuel. It's the crystalline polystyrene cups in a corrugated carton, otherwise known as the FM standard plastic commodity. It was put in an array of 2 by 6 by 3 cartons high. So your total height of storage was 1.6. Again, this isn't a warehouse operation. We're looking at providing the fuel loading that might be that you might see in a convention center exhibit hall. The sprinklers that were installed were on 3 by 3 spacing, okay, standard spacing, and they were pendant sprinklers. And the ignition was, as you see in the diagram, in the middle of the 2 by 8 array. The aisle is about 1.5 meters, and the other 2, what we call target arrays, is to evaluate whether the fire is of sufficient size that it actually skips over to the adjacent aisle. And what you're looking for there, will the fire continue to travel beyond its original ignition array? Again, within the facility, we had sprinklers, about 64 active sprinklers installed on 3 by 3 spacing. In tests 1 through 4, the ignition was directly underneath the sprinkler. And we do that because we're evaluating the delivered density from the sprinkler onto the burning array. Okay? When test 5 was conducted between 4 sprinklers. And we do that to evaluate the spacing to see if that is adequate. So, test number 1, Group A plastics. We first ran in a 12-meter high building. The fuel height remained constant throughout this test series at 1.6 meters. Okay? We used a K8 at a discharge density of 15 millimeters a minute. So the sprinkler was discharging at 1.5 bar. The first sprinkler operated at 1 minute and 53 seconds. You can see we had a total of 12 sprinklers. The last sprinkler operated at 6 minutes. You could see sprinkler number 45 was the first to operate. And then about a minute and a half later, the second sprinkler operated at 3:22. And then during the next 2.5 minutes or so, an additional 10 sprinklers operated. Now notice the operating sequence. This is something we see when we have high floor to ceiling clearance. The sprinklers directly east and west of the ignition didn't operate. Okay? That's called skipping. Skipping is a phenomenon where sprinklers activate outside its normal, or what you would consider to be the normal operating sequence based on the fire and the fire plume. When you have high clearance, unlike, let's say, out in the lobby there, when your sprinkler operates, the pressure will create a momentum. All right, so the sprinkler spray will reach the floor or the burning commodity, and primarily because of the momentum from the sprinkler spray. But when we have these very high clearances, that layer only lasts so long. Then the ability of the spray to reach the burning commodity is going to depend on gravity. Okay? But, so you have the gravitational forces from the water, but you've got the fire plume draft. It creates a drag on that. So not all the water that's discharged is going to reach the burning array. Some will get evaporated, and others will actually get carried upwards and wet surrounding and adjacent sprinklers. And that's quite often what we find when we have extreme or severe skipping. One of the tests that FM had done during their test program back in the 1990s, again, it was very similar where they had the ignition underneath the sprinkler, but none of that second ring of sprinklers around the one underneath the ignition sprinkler operated. Now we had the third and fourth ring operating. So this is a typical problem that we have when we have high clearances. So how do we combat that, or I'll discuss that a little bit later. Here you can see the temperatures. We have you can see early in the initial fire growth, where the temperature decreases is where the sprinkler operates at about 1:53. But the water does very little to control that fire, so the temperature increases. Test number 2, we increased the ceiling height to 16 meters, kept the sprinkler orifice size the same, and we increased the density from 15 millimeters to 20 millimeters. Okay? And we also changed the RTI. In test number 1, we used a standard response sprinkler. In test number 2, a quick response sprinkler. So we actually changed a number of variables in this test. 2 minutes, the first sprinkler operated. Now, that's interesting because we increased the building height 4 meters, but the first sprinkler operated essentially at the same time. That's because in this test we used a quick response versus a standard response sprinkler. And here again, we see the skipping. You see the initial sprinkler, number 45, operated at 2 minutes. And then 2 other additional sprinklers operated, the last one being at 5 minutes and 44 seconds. The fire spread across the aisle and down the array and was not controlled. Okay? So only 3 sprinklers operated, but that wasn't sufficient in order to control the fire. So what happened here? We increased the density, but what we did was we decreased the droplet size. The droplet size from a sprinkler is directly proportional to the orifice of the sprinkler, and it's inversely proportional to the pressure. So as we increase the pressure, we're going to decrease the drop size, even though we're increasing the total amount of water that's discharged. Test number 3. Oh, I'm sorry. This is the test number 2 temperature results. You can see first sprinkler operated, but when you look at the red and black lines, the temperature continues to increase, and we terminated the test after about 7.5 minutes. Okay, test number 3. Again, we kept the ceiling height the same, 16 meters, but we used a different sprinkler. Instead of a K8, we used a K11 sprinkler, and we increased the density a little bit. We went from 20 millimeters a minute to 23. And this is, we're back to 1.5 bars. At the previous test, I guess I should have mentioned, we increased the pressure to 2.5 bars in order to give the 20 millimeters a minute. Oh, okay. Here, we only had 1 sprinkler operate. it operated at 2 minutes and 44 seconds and actually did a pretty good job of controlling that fire. So with that orifice size and that discharge pressure was adequate to control the fire within the 16 meter building. As you can see, the temperatures after sprinkler operation remain fairly constant. For test number 4, we went to 18 meter building, and we really increased the orifice size of the sprinkler. We used what's a metric K360, or what we know as a K25. At a 1 bar pressure, that means the sprinkler is discharging at a density of 40 millimeters a minute. That's a lot of water. Okay? And it's a standard response sprinkler. Only in test number 2 did we use a quick response sprinkler. The first sprinkler operated at 334. You know, we'd expect that. Again, the fire is going to be a larger size because of the higher clearance. 1 sprinkler operated and controlled the fire, as you can see by the temperature curves. Test number 5 also utilized a K25 at 1 bar, but here, instead of the ignition being directly underneath the sprinkler, it's between 4 sprinklers. We want to see if anything adverse is going to happen because the fire isn't located directly underneath the sprinkler. In other words, how many sprinklers, in fact, will operate. And in this test, we operated 3 sprinklers, 3 of the first ring sprinklers. The first one operated at 311. The last one at 314. So that's very good. You know, that's good because you get almost simultaneous operation of the sprinklers. That's very effective for fire control. There's the temperature curves. You basically return to ambient after the temperature or after the sprinklers operate. So, to summarize, in order to control the fire in these high clearance, or actually, it applies to anything. You have to have enough water delivered onto the fire, okay? And when you have these high clearance facilities, it's very critical that you get a large enough orifice size in the sprinkler in order to create a droplet that has an ability to penetrate the fire plume that's going to develop because of the clearance. Again, as I said, when you're at these clearances, it's not the sprinkler momentum or sprinkler spray momentum that is going to be the main control mechanism. It's going to be the gravitation forces from the droplets themselves. So under a 12 meter ceiling, a K8 sprinkler at 15 millimeters did not control the fire. When we, at a 16 meter ceiling, the K11 sprinkler at 20 millimeters per minute did not control the fire. And when utilizing a K11 sprinkler, it marginally controlled the fire at 23 millimeters a minute. Now, had we increased the density of the K8 to 23 millimeters a minute, do you think we would have been successful? No, we wouldn't. We'd actually gone the other direction. The droplet size is going to be smaller. And then under 18 meter ceiling, the K360 or K25 did a very good job at 40 millimeters a minute. So, where are we at from the standard standpoint? Again, looking back, well, we know some of these are inadequate and some changes have been made. Now, China, they're changing their standard to include these very high densities. I realize 40 millimeters a minute is a lot of water. And that's all based on risk analysis. FM did some fire tests in their series, and I'm trying to think. They used a K11 at a density of 18 millimeters a minute in a 18-meter building and was successful. But 13 sprinklers operated, okay? If you're comfortable with that, that's fine. In fact, that's what's in FM data sheet 3-26. Now, the Chinese government, they weren't as comfortable with that. They wanted more of a suppression sprinkler or design criteria, and that's why the higher densities. So I didn't come here to tell you what to do or how to protect these various occupancies, but you do have to understand the characteristics of the sprinkler and its spray in order to, develop adequate protection criteria. I went to Singapore, and because we're in a standards revision process, and they wanted some guidance based on the tests that we did in FM. And what's funny is that after we presented the data, they proposed change was 12 millimeters a minute over 360 square meters, utilizing a K11 sprinkler. The fire tests that FM did and we did, indicate that that's not adequate. But their position was funny. They said, well, we didn't have any criteria before, so now we do have some criteria, and that's an improvement. Okay? So you have to be careful. Anyway, actually, of the existing standards, FM 3-26 is an excellent document on how to protect these types of facilities. All right, thank you.